Good day, viewers across the globe. I welcome you to my class today on numerical analysis. We shall be looking at part 2 of the topic we started in our last video, interpolation. We shall be looking at part 2 of interpolation today. Interpolation is a vital part of numerical analysis that helps us to carry out estimation. It also helps for prediction and forecasting. And in a situation whereby a set of tabular values are given and the function is not known explicitly, we can use interpolation to get the function or a function that is closely related to it. Beloved, my name is Dr. Chris Esekaigbe. I want to welcome you today to my YouTube channel, Dr. Chris Esekaigbe, where I teach mathematics and statistics topics to be part of those sharing knowledge across the globe. I am a chief lecturer in one of the most prestigious polytechnics in Nigeria. I am a chief lecturer in one of the most prestigious polytechnics in Nigeria. I hold a doctorate degree in mathematics and a master's degree in mathematics and a bachelor's degree in statistics. My area of specialization is numerical analysis. I do a lot of numerical analysis. I specialize also in data analysis and modeling. You can consult me for your scientific computing, your statistical research, and I like partnering, working with people across the globe. If you have any challenge or you are doing a research in any area in numerical analysis, statistical analysis, data analysis and modeling, you can consult me and I'll be part of your work. Or peradventure, you are a research institute across the globe and you deal on research, you do statistical analysis, all manner of research. I can be part of your research work, especially doing analysis for you or joining your team of analysts to do whatever analysis you are doing. I specialize also in analysis, numerical analysis. So if you are also an AI firm that specializes in developing models, I can be part of what you are doing. We can work as a team and develop advanced models, mathematical models and mathematical algorithms for artificial intelligence. Why not contact me so that I can be part of what you are doing? I live in Nigeria. I work in Nigeria. I have wealth of experience. Over the past 20 years, I've been teaching and lecturing mathematics, courses in mathematics and statistics. I also have university experience. I've lectured in an open university here in Nigeria, and I've also lectured in an A-level college, a pre-university college in Abuja, Nigeria, where I taught students Cambridge mathematics and I produced students with grade A. I also taught in OSSD, the Ontario Diploma, where I produced students also with grade A. I taught advanced calculus and advanced functions, and I also taught in IFG, that is partnering with UK, the International Foundation Group, in that pre-university in Abuja, Nigeria. So whatever you see me do in this YouTube channel is as a result of my wealth of experience. So I want to share this experience across the globe. Once again, my name is Dr. Chris Esekaigbe. I am a chief lecturer in one of the most prestigious polytechnics in Nigeria. I hold a doctorate degree in mathematics, a master's degree in mathematics, and a bachelor's degree in statistics. Here are my contacts. I have 2 contact numbers. They are also WhatsApp numbers. You can reach me on this number, +234 80 21903, or +234 7066 297535. These two numbers are also my WhatsApp numbers. You can send me WhatsApp messages, or you can reach me on my email address, chrisdavids2015@gmail.com. I have written quite a number of books. I've authored quite a number of books. A first course in numerical analysis, functions and geometry for undergraduate, mathematical methods for undergraduate, linear programming for undergraduate, and also authored two good books in statistics, applied statistics for business, sciences and engineering, volumes 1 and 2. My students find this book impactful in their various courses. So please, I also have publications, national and international publications, and I've also presented papers in renowned conferences across Nigeria and across and outside Nigeria. So contact me so that we can do your research together, so that I can be part of your artificial intelligence firm or your research institute across the globe. God bless you. So today we shall be looking at interpolation part 2. We shall first of all be using the Newton's forward difference interpolation formula to solve a real life problem. We want to see how this thing can be used to solve a real life problem. Permit me to clean up my details on the board. Reach me. I'll be waiting for your call. I'll be waiting for your emails. I'll be waiting for your WhatsApp messages. And as you do, God will bless you. Let us join our hands together in sharing knowledge across the globe. Mathematics and statistics are very interesting. They are very interesting. So we want to see how we can use this formula to solve a real life problem. In our last video, when we talked about interpolation part 1, we considered two examples. The first example, we solved a problem using the Newton's forward difference interpolation formula. Then we also solved another problem. That first problem was having h, the mesh size for x. Then the second problem was not having a mesh size for x. There was no h. So we resulted in using the Newton's general interpolation formula, also known as the Newton's divided difference formula. So those two examples were example 1 and example 2. So today we are looking at example 3. Example 3, we are looking at example 3 today. Now let's take this problem. The population of a country, in different census is given below. So let us say the population. Now we are going to have the years. The years are in X. Then we are going to have the population. The population is in millions. We are going to call that our Y. So permit me to write it this way. So we have the first year 1981, then the second one 1991, then the third one 2001, then the next one 2011, then the last one 2021. So these are the years we are going to be considering. Now the question is, we are to estimate the population for the year 1985. So we have to estimate the population for the year, estimate population for 1985. That is the question. So now, the first thing we are going to do is to create our forward difference table. Now, the population in millions, here we have 46 million. It has been narrowed down in millions. Here is 66 million. And the other one is 81 million. And this one is 93 million. And the last one, 2021, is 101 million. So this is what we have, the population in millions for the particular country. Then X represent the years. You know, census is done every 10 years. Between 1981 and 1991 is 10 years. Between 1991 and 2001 is 10 years. Between 2001 to 2011 is another 10 years. Between 2011 and 2021 is another 10 years. So now, without being told, you will know that from here, our age is equal to 10. Now, the problem that we have to solve, which is the estimate we have to get, that means our X will be 1985. Then remember, this will be our X naught. Our X naught will be equal to 1981. So remember, this is X naught, X1, X2, X3, X4, Y naught, Y1, Y2, Y3, Y4. So that's how the values are given. Now, let us get our first forward difference. 66 minus 46 is 20. 81 minus 66 is 15. 93 minus 81 is 12. We put it at the middle. 101 minus 93 is 8. Now, the second forward difference, 15 minus 20 is minus 5. 12 minus 15 is minus 3. 8 minus 12 is minus 4. Then the third forward difference, minus 3 minus 5 is plus 2. Minus 4 minus 3 is minus 1. Minus 4 minus 3 to be minus 4 plus 3, and that will be minus 1. So of course we will get a fourth forward difference. Then minus 1 minus 2 will be minus 3. So this is what we have been able to do. So we have successfully created a forward difference table. We have successfully created a forward difference table. So it will be good we come to this side. If you look at the first thing we need to do is to get our P from here. So our P will be equal to X. We have to estimate from this given table of census result for 1, 2, 3, 4, 5 for 5 years. We are now to estimate the population for year 1985. Look at it now. 1981 is 46 million. Remember, this thing was reduced in million, so it is in million. Then 1991 is 66 million. So you can see that 1985 is in between 1981 and 1991. So it is forward. If peradventure we are told to look for year 2015. 2015 is in between 2021 and 2011. So it will be between this. So we will now consider the backward difference. So now we are looking at the forward difference because this 1985, this particular formula is a real life problem. This is a real life problem we are we can forecast the population of a nation even when census is not done, when we have records of census data. We can use interpolation to estimate the population for a particular year once we have census data for some years. So these things, they are applicable. Numerical analysis is what we apply in solving real life problems. They are not things that are not real, they are real. So this is an example of a census result from a particular country. And you can see now, they took census in year 1981 and they got 46 million. They took census in 1991 and they got 66 million. They took census in 2001, they got 88 million. It was on the steady increase. You can see that the population of that particular country is on the steady increase. Now, if you want to estimate the population for 1985 is above 1981. If 1981 is 46 million, that means that for 1985 is expected to be above 46 million. You can see it's on the increase. But you can see that 1991 is above 1985. So it is not expected to be 66 million. The population for 1985 is not expected to be 66 million. It's supposed to be in between these two values, in between 46 million and 66 million. So the first thing we are going to do, now we have an idea of what the result will look like. If you calculate the population for 1985 and it's lesser than 46 million, something is wrong somewhere. But because you can see that the population is on a steady increase from 46 million to 66 million to 81 million to 93 million to 101 million. So let us calculate our P. So the X is the year we want to estimate for. X is 1985 minus our X naught, of course, is the first one is 1981 all over H. X minus X naught all over H. H is 10. So if you say 1985 minus that will be 4 over 10. So our P is equal to 0.4. So our P for this particular problem is 0.4. So permit me now to start this application. So now we want to get for year for year 1985 using this formula. For year 1985, so we are going to start this way. Now our Y naught, of course, is 46, then plus P, our P is 0.4 into the first change is 20 into 20, the first forward difference, then of course plus P is 0.4 into 0.4 minus 1 all over 2 factorial is 2, then the second forward difference is minus 5, bracket minus 5, then again plus P is 0.4 into 0.4 minus 1 into 0.4 minus 2 all over 3 factorial. 3 factorial is 6. Then our third forward difference is 2. So you put the 2 in bracket. Then you come again plus, of course, there is a last one. P is 0.4 into 0.4 minus 1 into 0.4 minus 2 into 0.4 minus 3 all over 4 factorial is 24, then bracket open minus 3. So that is what you have. So these are the arithmetic that we are going to be doing one after the other. So you have seen the question, and now I want you to permit me to clean this question so that we can write we can have space, enough space to write. Our P is already 0.4, so it's taking. Permit me to also clean this part of the board so that we can have enough space to write. Now, if we are to continue, our Y of our year 1985 will now be equal to, the first value there is 46, plus now 0.4 times 20 will give you 8 plus 8, plus, if you carry out this arithmetic, (0.4) minus 1 times minus 5 times 0.4 divided by 2, you are going to get 0.6, plus, then you carry out this one, 0.4 minus 1 into 0.4 minus 2 into 0.4 multiplied by 2, then you divide it by 6, you are going to get 0.128. 0.128 plus, then if you carry out this arithmetic, 0.4 minus 1 into 0.4 minus 2 into 0.4 minus 3 into 0.4, then multiply by minus 3, you are going to get 0.1248 plus 0.1248. So permit me to continue here. Year 1985 will now be equal to, if you add everything there, you are going to have 54.8528. 54.8528. So we can now approximate to 2 decimal places. Year 1985. Okay, let me write it in full. Year 1985 will be equal to 54.85 million. So this is what the population of that country will be in year. So the estimated population for that country in year 1985 will be 54.85 million. So you can see 54.85 is between 46 million and 66 million. So we are on track. So you can see how we have been able to use interpolation to estimate the population, the population of that country for a particular year where census was not taken. A census was not taken in year 1985, but as a result of the records in all the previous census from 1981 to 2021, we have been able to estimate the population of that country for year 1985. That is what interpolation can do. It helps us to estimate, it helps us to predict, to even forecast into the future. So these are applicable in real life situations. Peradventure in your country, you can calculate, it's possible to estimate the population of your country in a year where census did not take place. It is very possible. You have an estimate of the population in your country for that particular year. We can do it, you can do it using interpolation. All you just need to take the census data for some years, for many years. You can even take the whole of the years that the census was taken. You put it in tabular form like this, the year and the population. Then you begin to predict and you begin to estimate. You can use interpolation to estimate. You can see for this particular country now, I've been able to estimate the population of that country for year 1985, where census was not taken. Census wasn't taken in 1985, but we have it to be an estimate of 54.85 million. 54.85 million. We can also go ahead to estimate for this same country the population of that country for year 2015. And 2015 is in between 2011 and 2021. So let us go right away and estimate the population for year 2015. Permit me to clean this part. We want to estimate the population for year 2015. So you can say these are applicable to real life problems. By the time you know what census data are, they help to plan, and they help government. You can also use these to estimate, to do estimation for government, for different parastatals, real estate, in medicine, whatever thing you want to do, you want to estimate. Once you have a set of data, you can go ahead and do that using interpolation. Now, if you take a look at this formula, if we are to estimate for year 2015, now the formula we are going to use is what we call the backward interpolation formula. So now we are going to use the Newton's backward interpolation formula. For the backward, we use the backward operator. So permit me to change it. The backward operator is this. So we are going to put the backward operator here. You will see that we are removing the forward operator. So the backward operator will be this, and the square is there. So we are putting the backward operator, and the cube is here. We are putting the backward operator. So that's the backward operator. And please, when you are dealing with the backward operator, it's now positive sign all through. It will be p plus 1, p plus 2, p plus 3. This will be p plus 1, p plus 2, and so on. So the negative sign will turn to plus. That's just the difference between the backward and the forward difference operator. So you can see how this works. Now, yeah, you are going to have your p. Your p will now be equal to your x minus xn all over h. That is what your p will be. Now we want to estimate the population for the year 2015. So our x here will be equal to 2015. Remember, our xn is the last value of x. So our xn will be equal to 2021, which is here. Of course, our age remains 10 because the census was conducted every 10 years, and you will see it here as x increases, as the years increases. It was done in 1981, then next 10 years, 1991, it was done. Then 10 years after again, in 2001, it was done, and 2011, it was done, and 2021. So you can use this to forecast. If you have census data for your country, or you work in a population census in your country, and you want to forecast the population of your country, or you want to estimate the population of your country in a particular year that census didn't take place, you can use interpolation. You can contact me, we can do it together. Now it is good we have value for our p. Our p will now be equal to our x is 2015 minus 2021 all over 10. This will be equal to minus 6 over 10. So our p here will be equal to minus 0.6. So our p is minus 0.6. So what we are going to be doing, we are going to use this to carry out our calculation. We are going to carry out our calculation for year 2015. So let us go ahead now. This is the formula, the Newton's backward difference formula. permit me to write it here. Now change this to backward. This is backward. So you can see the backward difference operator pointing down, pointing down, pointing down, like that. And here, instead of for the forward difference operator formula, for the forward difference formula, it was plus, plus, p plus, p plus. But for the backward difference formula, it is p. For the backward is p plus, p plus, p plus. For the forward, it was p minus, p minus. And you can see for the backward difference operator is there. So when you have this operator up like this one is for forward. When you have it down like this one is for backward. So take note of that. So you can see this one pointing down, the arrow pointing down, so it is for backward. You have to change that and change the sign. That is just the difference between the Newton's forward difference interpolation formula and the Newton's backward difference interpolation formula. Now let us go ahead and calculate. So for year 2015, we are now using the backward. 2015 is in between 2011 and 2021. Please, I want to welcome you once again to my channel. Be patient to watch this video to the end as we deal on interpolation. Subscribe to my YouTube channel, Dr. Chris Esekaibe. Subscribe to it, share my videos on your social media platform, like my videos, and as you do, God will bless you. Be part of those sharing knowledge across the globe. The essence of this channel is to share my wealth of experience across the globe. Thank you very much. So let us continue. So for year 2015, we are starting this one. Sorry, this will be yn, not y naught. So for the formula is yn. You can see it now. It goes like that. So now you have this. You are going to have, and all this will no longer be y naught. It will be yn. It will be yn. It will be yn for the backward difference formula, and it will be yn. So if it is forward, you can put y naught. So this one is yn because it's coming from behind, so it's backward. So now let us go. Now we are starting with our yn. What is our yn? Our yn here is 101. Remember, y naught, y1, y2, y3, yn. So our yn, the last value of, because 2015 is in between 2021 and 2011. So we'll put our yn, which is the last value of y, will be 101. Then of course, you put your plus. Our p is minus 0.6. Then the first change, backward change, is 8. So you put it bracket 8. Then of course you put plus, you open a bracket. Now p is minus 0.6 minus 0.6 into minus 0.6 plus 1. You close the bracket, you close the bigger bracket. All over 2 factorial, 2 factorial again is 2. Then the backward change, of course, is minus 4. You cover the bracket. Then again plus bracket open minus 0.6 into minus 0.6 plus 1 into minus 0.6 plus 2. You cover the bracket. Then all over 3 factorial. Again, 3 factorial is 6. 3 factorial is 3 times 2 times 1, which is 6. If I say 3 factorial, this means 3 times 2 times 1. If I say 2 factorial, and that is 6. If I say 2 factorial, that is 2 times 1, and that is 2. If I say 4 factorial, that is 4 times 3 times 2 times 1, and that is 24. I hope that is understood. So that's what we mean by factorial. So there's a topic in algebra that is called factorial notation. I hope that particular part is taken care of. So let me go and continue with what I'm doing. So now you can see we are still using this forward difference table. Why are we using the forward difference table? Because the signs has been taken care of. P minus has now been changed to P plus. So it has taken care of the sign. Although you can also create a backward difference table, but you can use the forward difference table because this P plus, changing the negative sign to positive sign, has taken care of, has already changed it from backward, from forward to backward. Now you can see we have written this one. Now the third backward difference is starting from -1. So you put the -1 here. Then of course you come to the last one, plus -0.6 into -0.6 plus 1 into -0.6. Okay, let me take it up a little. Plus bracket -0.6 into -0.6 plus 1 into -0.6 plus 2 into -0.6 plus 3. You cover the bracket and you cover the bigger bracket. There's a bigger bracket here that needs to be covered. Then of course all over, you come here now. 4 factorial is 24. And again, the last value, which is the fourth backward difference, is -3. So you put this -3 in bracket. So you have that. Now we are going to take them one after the other. We are going to break them down. So you are going to write here 2015 will now be equal to, our first value here is 101. Then of course plus, when you carry out this, okay, it will be minus, because minus 0.6 times 8, that will give you -4.8. -4.8. So permit me to clean this part of the board so that we can do a very neat job. So for year 2015, we have 101. Of course, it will minus 0.6 times 8 is -4.8. Then now you come to this other one, -0.6, 1 is -0.6 plus 1, minus we cancel minus, of course it will become plus. So when you carry out that arithmetic, you have plus 0.48 plus 0.48. Then you come again to the next one. If you carry out this will be positive, this will be positive, minus, of course, we turn to positive. Then you divide it by 6, so everything will give you positive. When you carry out that arithmetic, you get plus 0.056, plus 0.056. Then you come to the last one. Of course, this will give you plus, this will give you plus, this will give you plus. So minus and minus again we cancel, so you will get positive. So you are going to get, and you divide by 24, you are going to have 0.1008 plus 0.1008. So these are the arithmetic we have done then. So when permit me to write here, year 2015 will now be equal to, carry out that addition, you are going to get 96.8368. 96.8368. 96.8368. So in two decimal places, the population for that country for year 2015 will be equal to 96.84 million. You see that? So you can see this is year 2021. 2015 is in between 2011 and 2021, between 93 million and 101 million. So that is where 96.84 million lies. So we are on track. So you can see from this census data, we have been able to predict or estimate the population for this particular country for year 1985, and we got a value 54 point something million. We got 54.85 million, and we have also done that for year 2015, and you can see 2015 lies between 2011 and 2021, and for 2011 is 93 million. Of course, for 2015 is expected to be higher than 2015 is expected to be higher than that of 2011, because you can see there's a steady increase in the population in millions for this particular country. So the population for this country for year 2015 is 96.84 million. So we have been able to do justice to this. I believe you have learned how to use interpolation to estimate, to carry out estimation. Now we want to quickly go and do something else. Now, what if you are given a particular set of data where there is no age? Like this one, we have age to be 10. That's why we are able to use the Newton's forward difference formula and the backward difference formula. So I know by now you know how to use the Newton's forward difference formula and the Newton's backward difference formula. You know the differences between the two formulae. And the first thing you need to do as a numerical analyst, when a set of data is given, you inspect the data visually. Inspecting this data visually, you can see that there's a common increase in the years, which is 10 years. It means for that particular country, census was done every 10 years. And again, you can see, check the population in millions, you can see that there is a steady increase in the population growth. So whichever year you calculate, you don't expect the previous year to be higher than the year you calculated. That is how you study as a numerical analyst. You see, my knowledge in statistics has really helped me a lot in numerical analysis. That's why in my first degree I did statistics, and I know a lot of data analysis and data modeling, and then this now enabled me to do my master's and my PhD in numerical analysis. This has helped me a lot. It has helped me to be a better statistician, and it has helped me to be a very good numerical analyst. So why don't you connect with me so that we can work together as a team in your research institute in any part of the world. God bless you as you do that. Now I want to go to another part, which is the Newton's general interpolation formula. We have to use that in the situation whereby the age is not given. Permit me to rub this off. Well, we want to look at the Newton's general interpolation formula. We want to see how we can also use the divided difference. So when age is not given, you resort to using what we call the Newton's general interpolation formula, which is also known as the divided difference formula. So the divided difference formula. So now general interpolation formula, and this formula is also called divided difference formula. So we want to see how we make use. This formula can also solve a problem having h. It can also solve a problem that is not having h. So it's the Newton's general interpolation formula, and this formula is given as y equals y naught plus x minus x naught. Then the bracelet is from the divided difference table. The bracelet is x naught x1, then plus x minus x naught into x minus x1. Then again the bracelet is open, x naught x1 x2, and then again the plus x minus x naught into x minus x1, of course it continues, into x minus x2. Then of course you open the bracelet, x naught, x1, x2, then it keeps going like that. Of course you can take almost a plus x minus x naught into x minus x1 into x minus x2 into x minus x3. Then the bracelet is for x naught, x1, x2, x3, comma, then plus, it continues. So it keeps going like that and like that. So this is the Newton's general interpolation formula. It is also known as the divided difference formula. Now we want to take example 4. In our fourth example, a table is given of x and f of x. X, f of x. The f of course, you know that your y is a function of x. So you don't need to be frightened about that. So when you see your f of x, you are talking about your y. Of course, this one is also for f of x. So now we have the values for x as -1, 0, 3, 6, and 7. These are the values for x. And our y, for y, we have 3, -6, 39, 822, and 1611. So that's what you have for your f of x. Now you have this table. You can see that for this particular table, your x is having -1, 0, 3, and so on and so forth. You will also see that x does not have a uniform difference. X doesn't have a uniform difference. 0 minus 1 is 1. 3 minus 0 is 3. 6 minus 3 is 3. 7 minus 6 is 1. So it means that we cannot use the forward or the backward difference formula. So that's why we are resorting to using the divided difference formula, otherwise also known as the Newton's general interpolation formula. Now let us get the first divided difference. This is how it goes. -6 minus 3 is -9. -6 minus 3 is -9. 0 minus -1 is 1. So -9 divided by 1 is -9. Now again, 39 minus 6, of course, 39 minus -6 is 45. Then 3 minus 0 is 3. 45 divided by 3, of course, you have 15. Then now, you will see 822 minus 39. 6 minus 3 is 3. So 822 minus 39, you divide the answer by 3, you will get 261. Here again, 1611 minus 822, of course, you will get 289. 7 minus 6 is 1. Divided by 1, it remains itself. So you have 789. So now we are going to the second forward divided difference. Now you have What gave birth to these two is from year to year. You can see it, minus 1 and 0 give birth to this minus 9, that is 3 and minus 6. Then minus 6 and 39 also give birth to this 15. So when we are considering minus 9 and 15, we are considering from 3 to minus 1. So 15 minus 9, that is plus 24. So 3 minus 1 is 4. 24 divided by 4, you have 6. Then again, what gave birth to these two is from year to year, from 0 to 6. So 261 minus 15, then 6 minus 0 divided by 6, you will get 41. Then again, what gave birth to this is this. What gave birth to this is these two values. Now, if you have this minus this, and you separate 789 minus 261, and you divide it with the difference between 7 and 3, you are going to have 132. That's what you have. Then you come here now for the third divided difference. Now, what gave birth to this is from year to year. What gave birth to this is from year to year. So we are looking at from year to year. So 41 minus 6 is 35. So everything came from year to year. So 6 minus 1 is 7. So 35 divided by 7, you will get 5. So what gave birth to these two is from year to year. So 132 minus 41 divided by 7 minus 0 divided by 7, you are going to have 13. So now the last one, which is the fourth divided 4 difference, you are going to have it as, okay, there's no need for rolling a line. So 13 minus 5, what gave birth to this 5 is from this minus 1 to 6. Then what gave birth to 13 is from 0 to 7. So we are looking at from 7 to minus 1. 13 minus 5 is 8. 7 minus 1 is 8. 8 divided by 8 is 1. So we have successfully created our divided forward difference table. This is our divided difference table. Our divided difference table. Please subscribe to my YouTube channel, Dr. Chris Esekaibe. As you do, God will bless you. Share my videos, my YouTube videos on your social media platform. Like my videos. As you do that, God will bless you. Be part of those sharing knowledge across the globe. You can consult me for any research on numerical analysis. If you're a research institute, I can be part of that institute to do numerical analysis, data analysis, and modeling for you. And as you consult me, we work together as a team. Now let us go ahead and calculate and solve the problem. What we need to do here is to find, we have to find the function, find f of x that is given, that brought about this table. So that means our y is also f of x. So our f of x will be equal to, what is our y naught? Our y naught is 3. Then what is our x? Our x is there. X naught is minus 1. So x minus 1, it will be x plus 1. So you have plus bracket open x plus 1. Then this is divided difference. You have this minus 9 in bracket. Then of course plus. Then you come here now. The next one is x minus x naught. Of course our x naught is minus 1. So that will give us x plus 1 into x minus x1. x1 is 0, so x minus 0 is x in bracket. Then the second difference is 6. Then you come again plus. You come again now. Again, x minus x naught. X minus x naught. X naught is minus 1. X minus minus 1 is x plus 1. Then x minus x1. Our x1 is 0. This is x naught, x1, x2, x3, x4. So that one will be x again. Then we have x minus x2. Our x2 is 3. Then you put in bracket x minus 3. Yes, x minus x2. Then this one, the next one is 5. Then you put 5. Then you come again, you say plus. The last one, x minus x naught. X minus minus 1 is x plus 1. Then x minus x1 is x minus 0, which is x. Then x minus x2. x2 is 3, so you have x minus 3. Then the next one is x minus x3. That will be x minus 6. x3 is 6. You see it there? Then the difference, the divided difference will now be 1. That's what you have there. So this is x0, x1, x2, x3, and so on and so forth. So that's how we have. So we are going to open up the bracket one after the other. If we open this, our f of x will be equal to 3. If you open this, you are going to have minus 9x minus 9. Then if you open this, you are going to have 6x squared plus x plus 6x squared plus 6. And if you open the next one, you are going to have plus 5x raised to the power 3 minus 10x squared minus 10x squared minus 15x. Then when you expand this one, you are going to have plus, let me continue it here, plus x raised to the power 4 minus 8x raised to the power 3 plus 9x squared plus 9x squared plus 18x. Now you can see what we have there. So if you take the like terms, you will come together and have your f of x to be equal to x raised to the power 4 minus 3x cubed plus 5x squared minus 6. So you can see that is what you are going to have. S raised to the power 4 minus 3x cubed plus 5x squared minus 6. You can see the divided difference table stop at the fourth forward divided difference. That is why the polynomial is of degree 4. If it stops at 3, for instance, the polynomial will be of degree 3. But here it stops at 4. So if it stops at 5, it will be a polynomial of degree 5. So this is one way you use to know whether it's going to be a quartic polynomial, a quintic polynomial, a cubic polynomial, or even a quadratic polynomial. So, but now it stops at the fourth divided. The divided difference table stops at the fourth forward divided difference. Hence, we are getting a quartic polynomial, a polynomial of degree 4. Now, one good thing about this, these table values of x and f of x were given. You can call it. You can also call this y. They are given, but f of x is not known explicitly. But you can see how we have been able to use the Newton's general interpolation formula even when h is not known. Even if h is known, you can still use this formula. You can see how we have been able to use the Newton's divided difference formula to get the function that was not originally known. Now, if you want to test, if you put f of minus 1, look at it now, you want to test, if you put f of minus 1, you are coming here to get minus 1 raised to the power 4 minus 3 into minus 1 raised to the power 3 plus 5 into minus 1 square minus 6, and of course that will give you 3. It will give you the value of 3. If you want to try f of 0, so you can see that this particular polynomial represents this data set very well. If you want to get f of 0, it's going to be 0 raised to the power 4 minus 3 into 0 raised to the power 3 plus 5 into 0 square minus 6, and this will give you minus 6. You see it here, when x is 0, y is minus 6. You come here, you try your f of 3. F of 3 will be 3 raised to the power 4 minus 3 into 3 raised to the power 3 plus 5 into 3 square minus 6. If you put these values in, you will get 39. If you also put f of 6, if you put f of 6, you will get 822. If you put f of 7, you will get 11611. That's what you are going to get. So now we can also use the same polynomial to predict for the value of x when s is 8, 9, and so on. So permit me to clean this part of the board as we forecast for more values of x. So you can see that interpolation helps us to forecast. It helps us to predict. It helps us to forecast. It helps us to predict. Now you can see in between 3 and 6. 3, when x is 3, f of x is 39. When x is 6, f of x is 822. You put these values in as I have put these other values in. Now I want to try when x is 4. When x is equal to 4, so our f of 4 will be equal to 4 raised to the power 4 minus 3 into 4 raised to the power 3 plus 5 into 4 square minus 6. If you carry out this, you will find out that you get 256 minus 192 minus 192 minus plus 80 minus 192 plus 80 minus 6. This is equal to 138. So you can see when x is equal to 4, here you will have f of x to be 138. We can also try f of 8. We are predicting. So this will be 8 raised to the power 4 minus 3 into 8 raised to the power 3 plus 5 into 8 square minus 6. And when you have that, you are going to have 2,874. 2,874, which is above 1,611 when x is 7. So beloved, you can see how far we have gone today. So this brings us to the end of the topic interpolation. We have been able to solve a real life problem on census using the Newton's forward or backward difference formula. We have been able to find a function f of x that is not known or that was not known originally when the data set was given, and we have been able to predict or estimate future values of x. You can see for this example that we treated, x stops at 7, but we're able to estimate the value of x, the value of f of x when x is 8. So you can see that doing this is very, very useful to us, and interpolation helps us to predict, it helps us to estimate, and do all manner of solve all manner of life problems. So please, once again, subscribe to my YouTube channel, Dr. Chris Esekaibe. Click on the bell button for notification each time I upload a new video, and also like my videos, share them on your social media platform. I'll be coming again with a new topic in my next video. I will be looking at linear regression. Now I want to move a little into statistics. There is what we call curve fittings in numerical analysis. When we talk about curve fittings, we have what we call linear curve fittings and non-linear curve fittings. So I'll be connecting the linear curve fittings with linear regression. We'll be saying the similarities that they have. When you want to fit a linear model, you want to fit a straight line in regression analysis, and you want to fit a linear model in numerical analysis. What are the similarities? Are they the same? At the end of that class, you will be able to know if they are the same or not. The class will come in no distant time from now. Wait patiently for it. Watch this video to the end, and as you do, God will bless you. See you in my next class. Have a great day. Bye.